Good evening, classmates. Welcome to our reports. For our report, we will be reporting the tube system in tall building. So the report consists of part 1 and part 2. So for part 1, first is the tube structures. Second will be frame tube. Number 3 will be the brace tube structure. 4 is the bundle tube. And for part 2, hybrid tube system and super slender tall building design. Part 2 will be reported by Engineer Maria Olaguer. Our report is only frame tube structure. However, due to limited and reliable literature online and other resources, we found out that we better introduce the overview of the tube system structure to have a general perspective of this kind of system. Introduction of tube structures. In the tall building design, the tube system is one of the common lateral stability systems. It is designed to act as a vertical cantilever hollow shell cylinder. This allows to create an indefinite stiff shell around the building exterior. The system was introduced by Fazlur Rahman Khan from the firm Skidmore, Owings and Merrill in 1970s. It was an innovative lateral stability system for designing a taller, more efficient building at that time. It has dramatic difference compared to the traditional structural system for multi-story buildings, such as portal frame system, core wall strengthened by outrigger. The first example of tubes use is the 43-story Dewey Chestnut apartment building, Chicago, Illinois, was completed in 1966. Steel concrete or composite construction can be used for this type of system. For this particular type of system, the exterior framing should be designed sufficiently strong, normally in terms of rigid beam to column connections. The perimeter of the exterior consists of closely spaced columns that are tied together with deep spandrel beams through moments connection to resist all lateral loads. The distance between the exterior and the core frames is spanned with beams or trusses. Later on in this report, we can identify the core and the exterior frames. This can maximize the effectiveness of the perimeter tube by transferring some of the gravity loads within the structure to it and increases its ability to resist overturning due to lateral loads. The tube structures are categorized in several different types: tube in tube, frame tubes, brace tube, bundle tube, hybrid tube system. The construction method in this type of system, the tube system, is similar to the construction of the shear walls and rigid frame. Due to the trade secrecy and privacy of the various contractors and designers, most of the step-by-step methods was not published online. For the sake of the report, a case study, application, and lesson learned will be best suited for this type of reporting. So for this case, let's start with the tube in tube case study of Petronas Tower. So the Petronas Towers used to be the tallest building in the world. It is also known as the Petronas Twin Towers. They are twin skyscrapers in Kuala Lumpur. The architect of Petronas Tower was Cesar Pelli and Associates, and the structural engineering company was Thornton Tomasetti Engineers. Thornton Tomasetti used the tube-in-tube system design for this iconic building in Malaysia. Petronas Tower Structural System. The building is built primarily in concrete. Most of the structure members are made with high-strength concrete. According to some journals, the Petronas Tower used the 80 megapascal concrete. High-strength concrete was used in central core, perimeter columns, perimeter ring beams, and outrigger beams. The two towers are connected through a sky bridge. The foundation of the tower was constructed using 104 concrete piles. The tower sat on a large concrete raft. So this is the structural system of the Petronas Tower. The structural system of each tower comprises a 25 by 25 meter central core and an outer ring of widely spaced of 16 cylindrical super columns. So the one circling the core, these are the 16 cylindrical super columns. These 16 cylindrical columns are constructed using high-strength reinforced concrete. These columns are linked by ring beams to build a moment frame outer tube. This is one of the good examples of tube-in, tube systems, as there is a pair of soft tubes. So figures 4.5 to 4.7, later on in this report, we will see the 4.5 to 4.7 figures. These figures further demonstrate the structural arrangement of the Petronas towers. In between the outer tube and the inner tube, concrete beams are also used to connect them. In addition, steel beams are also used. However, they are primarily used to support the floor slabs. Figure 4.4 demonstrates the center tube and the outer tube of Petronas towers. So according to the journals that we have read, the data that they gathered, they put it in the ETABS, they made their own analysis, but the exact data coming from the real designers, real architects, they were not able to gather those data, but for the sake of their report, their report is already enough to check the integrity of the building, to check the deflection of the building, to check the possible maximum shear and maximum moment of that building. So the data that they gathered according to their book is already enough for the study. So figure 4.5, ground floor plan layout of Petronas. So as you can see, the core is still there, and we can see later that the core is still consistent up to the very height of the building. As shown in figure 4.6 is a sky bridge between the two. The bridge is supported on the two towers, which is pin connected to the towers, so allows them to move freely. This avoids the damage to the bridge when large movements occur between the two towers. So figure 4.6, it shows the layout, plan layout, and in figure 4.7, it also shows the layout in the story 80. So the core is still consistent from ground up to the very height of the building. In their analysis, in figure 4.8, shear force and overturning moment distribution during earthquake. In the analysis, we observed that the lower portion of the building has experienced max shear and overturning moment, in which the building is responding as a vertical cantilever, as desired by the designer. So figure 4.9 shows the lateral displacement. In the top building, in the top floor, the probable displacement is around 50 mm, as shown in the graph. So this is the stress of the core wall under earthquake loading. Next is the frame tubes. Frame tube system is one of the most widely used tube system compared to tube-in-tube system. It featured a much stiffer exterior tube in this type of system. The stiff tube was achieved through closely spaced columns connected by deep spandrel beams which are firmly joined together to make the stiffer exterior shell. Depending on the structure, the spacing of the column is quite close, generally 1.5 to 4.5 spacing. Spandrel beam depths can range from 0.5 to 1.2 meters. The disadvantage of this type of structure is the huge cost. To be able to ensure the rigidity of the connection in the outer tube, high level of workmanship is needed for welding and high strength bolt connectors are required. The erection and the fabrication are also more expensive in terms of the working hours. Another drawback is the so-called shear lag. The picture in this report is the Twin Towers in America. So this is known for the collapse. This is known for the terrorist attack in September 11. So this is the typical floor layout of the World Trade Center. So as we can observe, in the exterior part, we have a very closely and tight packed columns, whereas in the core, we have a spacious distance between the two columns. Now, for the shear lag effect in frame tube system, shear lag effect in a tall building can be demonstrated as shown in figure 4.13. It shows a plan cross-section of a building with a moment induced because of lateral load. It shows the theoretical and real distribution of axial stresses in peripheral columns. Under lateral load, such as wind or earthquake, the whole structure works as a vertical cantilever. Therefore, the stress distribution in the cross-section should follow the theory of bending in figure 4.13a. Theoretically, this is supposedly the figure of the stress distribution. So, however, the real distribution, as we can see in the figure 4.13b, of these stresses is not linear. In the cross-section, magnitude of stress at the corner side is higher in comparison to the columns of the middle location. Therefore, in the flange of the cross-section, the stress in the middle columns is less than that in the corner columns. The same kind of nonlinear distribution of axial stress can also be observed in the web, the cross-section, as shown in figure 4.13. So here is the case study of the Twin Towers. The Twin Towers was a large complex of 7 buildings in Lower Manhattan, New York City, United States. It featured landmark Twin Towers, which was opened on April 4, 1973, and was destroyed in the September 11 attacks. It used the steel core and perimeter columns to create a relatively lightweight structure to resist the lateral loadings. Therefore, it was primarily a steel structure, as most of the major structural elements were steel members. For the sake of fire resistance, fire protection measures such as sprayed fire protection material and gypsum wallboard were used to protect some structural steel elements in the tower, including the core columns. For the internal core of the World Trade Center, rather than using a concrete core, a steel internal core was used in the World Trade Center. The core columns were connected to each other at each floor by large square girders and I-beams about 2 feet deep. The main purpose for using a steel core is to save the total weight of the building. This in turn also saves the cost of the foundation. The core contained 47 steel columns from the bedrock to the top of each tower. The size of the core columns at lower levels are 558 mm by 1371 mm steel box columns, which are reduced to 406 mm by 914 mm box columns at the upper third levels. The columns were tapered after the 66th floor and consisted of welded box sections at lower floors and rolled wide flange sections at upper floors. As shown in figure 4.14, the exterior tube was built using 60 high-strength perimeter steel columns, spaced closely together, which are connected by spandrel plates to form a strong rigid exterior tube, which were 64 meters long. Connection between exterior tube and the central core. As shown in figure 4.15, the perimeter tube and central core was linked by composite trusses floor system. The floors consisted of 10 cm thick lightweight concrete slabs on a steel deck with shear connections for composite action. The slabs were supported with trusses apart from resisting the gravity load. The floor system provides lateral stability to the exterior tube. The trusses are connected to the perimeter at alternate columns. The top cords of the trusses were bolted to seats welded to the spandrel on the exterior side and a channel welded to the core columns on the interior side. The floors were connected to the perimeter spandrel plates which are with viscoelastic dampers, which help to reduce the amount of sway by building occupants. Beside composite truss floor, hot trusses or outriggered trusses are also used from the 107th floor to the top of the buildings. The outriggered truss system consists of 6 trusses along the long axis of the core and 4 along the short axis. Connection between the exterior tube and the central core. In the figure, this is the ground floor of the World Trade Center. So in figure 4.18 shows the distribution of the column load at one edge of the exterior tube for the World Trade Center. Under the lateral wind load, it clearly shows the shear lag effect. The reason why there is a shear lag effect and also the reason why they have a nonlinear stress, it's because the beams also have their own stiffness. So with the different stiffness, most of the loads will be carried in the corners of the columns. So another type of tube structure, brace tube structure or truss tube structure. The brace tube is similar to the tube-in tube structure, but with comparatively fewer exterior columns. In most of the cases, steel bracings are used to compensate for the fewer columns by tying them together. By this arrangement, the overall cost of the building dropped dramatically. The advantage of brace tube is the diagonal brace can take the lateral load in axial action, thus reducing the shear lag. However, there are also some disadvantages, such as large brace block some windows. In addition, brace tubes are only used for structures with less than 60 stories, due to the fact that the external shell is not stiff as the frame tube. John Hancock Center in Chicago is one of the famous examples. Another is the bundle tube. When the height of the building increases, one tube is not sufficient to resist the huge lateral load that occurs from either earthquake or wind. Bundle tube is a structural system which consists of several tubes tied together to resist lateral forces. Such buildings have interior columns along the perimeters of the tubes when they fall within the building envelope. One of the famous examples is the Willis Towers. It consists of a set of singular tubes which are joined together to form a multi-cell tube structure, as individual towers are connected by belt trusses. It is especially suitable for the very tall structures. The bundle tube structure has the ability to reduce shear lag, hence provides a relatively lighter structure. So this is the floor layout of the bundle of the Willis Tower. So as you can see again, the core is still consistent from bottom to up. So what happened here, as the floor goes up, they just reduce some of the bundle tubes to reduce the weight, to reduce the shear lag, and probably for architectural purposes. Now this is the summary, the disadvantages and the advantages of every type of tube systems. So I let it flash here for a while so everyone can read it. And this is also the heights, the effective heights of the different structure system, tall building structure systems. Now for our references are coming from Ali M. and Moon K.S. Their book is the Structural Developments in Tall Buildings. Their journal is named Structural Developments in Tall Buildings. And for Fu F., the book he published is the Design and Analysis of Tall and Complex Structures. So that's it for me. Thank you, classmates, for listening. And if you have some questions, we will try to answer that on our meeting. Thank you.